Alright, so today in class we spent really most of the time talking about how the class would be graded and what we mean by this mastery grading, which is fine because I really think it's important that everyone knows how things are going to work and we're all on the same page, and I absolutely welcome any questions that you have after you've thought about it for a while. On the flip side of that, we didn't really talk about any physics today. So because I want the in-class portion to be a lot more active, we are going to have some videos that talk about sort of definitions and basic things that you're going to be watching outside of class, and then in class we're going to be really diving into it. It's just that getting ready for Thursday's class is going to be sort of extra work, simply because we're going to sort of try to catch up on things that we would have liked to do today, and then also talk about things that we're going to do on Thursday. We'll do that on Thursday. So that's what we're doing. So the first chapter we're going to do is what I like to call as one-dimensional motion, which is motion along a straight line. And so this can be motion that's horizontal or vertical, and it actually could apply to an object moving on an inclined plane. That's a straight line, it's just tilted, but if we tilt our head, it looks perfectly straight to us. So what we're really only thinking about is an object that can move in one dimension, up and down, left or right. That's what we're thinking about. And sort of this area of study is called kinematics, and it's just really the study of motion. And sort of what differentiates it from other things is when we're talking about kinematics, we're not really belaboring the reasons behind the motion. We're just kind of saying, okay, well, this is where the object is at this time, this is how fast it's going, this is what its acceleration is, and we use that information to describe the motion at other times, or to answer questions like how long did it take to go 50 miles, or that kind of thing. And so that's what we're going to be doing. This actually comes up in chapters 3 and 4, where 4 we're looking at two-dimensional motion. So the types of things that we're interested in when we're talking about the motion is, where is the object? How fast is it going? And is the velocity, which is how fast it's going, changing, which would talk about acceleration. These are all things that we would like to know. And the good place to start to get all the answers to these questions is to have, for a bunch of different times, knowing exactly where the object is, and we would call that information about where it is the position of the object. Now, let's just talk about the anchoring concepts of chapter 3. Remember, these are sort of the fine details of things that we should be able to understand by the time we're done with the chapter. So the things that you should know is you should know the difference between position and displacement, and distance, velocity and speed, and acceleration. So all these things you should be familiar with, as well as how you would calculate them, and also how they would be defined, which kind of is the same thing. You should be able to find the acceleration and velocity and how they depend on time if you are given the position as a function of time. You should be able to look at graphs of position versus time, velocity versus time, and acceleration versus time, and talk me through, like, what is this telling you about the motion of the object? How is it moving according to these graphs? And finally, near the end of the chapter, we're going to be looking at specific problems where we have constant acceleration, and we come up with some equations that we use for constant acceleration. And so this type of motion can be we could be describing a car that's moving and accelerating down the highway. At the same time, we could be talking about an object that is falling to the ground. Both of those would fall into that category of constant acceleration. Sometimes we talk about falling objects, like make that a more special category, and we call that free fall. Okay, so I wanted to do this demo in class, but I didn't have the chance. But let's say that I was looking at a ball rolling down a ramp, and I wanted to get some information about where is the ball at particular times. And what I ended up figuring out is I figured out places where the ball was and at equal time intervals. So the amount of time between, what we were doing is being able to hear the ball go down the ramp by putting dominoes that would get knocked over, and we would hear them fall, and this would tell us, okay, the ball is right there because it knocked the domino down. If we place the dominoes in a way that those falling is in equal intervals, we would actually find that the dominoes would be placed at these positions. So it means that the ball starts off, and in the first time interval it travels only 5 centimeters, but then in the next time interval it goes further, it goes 15, and then in the next second, if you will, if you want to call that time interval a second, it would travel 25 centimeters, and then we kind of keep on. So you're noticing that what's happening as the ball rolls down the ramp is it's actually traveling farther and farther in the same amount of time. And so that tells you that the ball is accelerating. We can sort of figure that out. And we probably expected that to be true anyway, because putting a ball on a ramp is essentially just slowing down the acceleration of free fall, and making it a little bit smaller acceleration, but it's still an acceleration nonetheless. So in any case, I know that it's really kind of stinks that I couldn't demo this for you, but let's just say that this is a graph of an object and where it was at particular times. This is kind of the type of information we would start with if we wanted to describe the motion of an object in great detail. And one of the best ways to sort of get the information from a table, which sometimes it's hard to see what's going on, is to make a picture of it. And the way we make a picture of it is we make a graph. And this graph is a graph of position versus time. And you can see the data points on this graph. I'm going to make them a little bit more obvious. And you can see that in equal time intervals, sort of the amount of distance that the ball traveled in, like, say, 1 second continually is increasing. Again, reflecting the fact that we know that the ball is accelerating. Now, we only really have the data at the blue dots that I marked on the graph, but we can assume that the motion would create a smooth line that would connect all those dots. And so we actually sort of produce a graph that gives us the ability to, at least to some degree of accuracy, sort of say that, oh, say at 2.5 seconds, I think that this is where the ball is. So making that graph gives us even more information about where the ball is at particular times. Now, the first thing that we're going to define is what is displacement. Now, displacement is going to be the term that we're going to work with the most, where distance might sound more familiar, but it's not really a measurement that we're going to use very much in physics. So the displacement is basically the change in the position during some time interval. And so we usually use this Greek letter delta. You're probably familiar with that as change. And so the change in x, if x is our position variable, delta x is just saying this is the difference between the x position at one time minus the x position at another time. And the way that we subtract is we always do final minus initial. Delta is always final minus initial, no matter what you're finding the delta of. That's always going to be true. Now, when we talk about distance, which is not something we're going to use too much in physics, distance is actually the length of the path that the particle's traveling in. And we'll show a sort of could be different. So for instance, let's say that I'm on a merry-go-round and the merry-go-round is rotating. And so as it rotates, this is the path. I'm not good at circles, sorry about that. This is sort of the path that I take. And this is where I start. And this is where I end. And so the path would represent the distance that I would move. But if this is like my origin, my position that I start with, this would be my x initial, and this would be my x final. And so actually, the displacement I would have would be x final minus x initial. Now, the way that I drew that, there's a lot of stuff going on here that I have to be careful with. And so, because I'm standing on a merry-go-round, I'm always going to be the same distance away from the center because I'm just standing there. And so let's say that this ended up to be 2 meters, but because it's in the up direction, I would call that positive. So this is 2, but I'm subtracting it. It's positive because it's up. But then the final position, because it's below the origin, I would call that minus 2. And so my displacement is actually going to be minus 4, because I kind of start 4 units below where I end up 4 units below where I started. But the path or the distance that I traveled would be different, because that would be equal to half the circumference of the circle. And so that would actually be like just 2 pi times 2 divided by 2. Because 2 pi r is the distance around the whole circle, and I'm just going to take half of that. So, I don't really like this example, but I had to keep going with it. Hopefully it makes some sense to you, but really what we're trying to look at here is that there is a difference between displacement and distance, and displacement is always going to be the term that we're going to be the most interested in. So that problem actually was good because it did introduce this idea of the signs, because I did talk about how the position when it was at the top of the path, I said that was positive, and when it was down it was negative, and also what the positive and negative signs meant in terms of where it is, because even though we're dealing with one dimension, we're only allowing something to move in a straight line. It has 2 possible ways it can go, and we really want to be able to differentiate them. What we're going to say is something, if I'm traveling in a horizontal line, as I go to the right, typically we say this is the positive direction, and typically we say to the left is the negative direction. Similarly, if we're going up, we usually say up is positive and down is negative. Basically, this is because we are we're dealing with what we call vectors. Vectors are quantities where their direction is important. And a lot of the things that we're talking about in one-dimensional motion, like position, displacement, velocity, and acceleration, the direction is very important. And we have to sort of make a differentiate between a car traveling to the right and a car traveling to the left. We have to indicate within its velocity how they're different, because you're going in different directions, and we typically do that with the sign of the velocity. We could also, with respect to their position, say that because the sign of its position will also tell us, where it is relative to our origin. Other types of quantities that don't have a direction, don't need a direction to describe them, are called scalars. And an example of a scalar would be time. Time doesn't have a direction. Also mass. Mass doesn't have a direction. Now you might say that I have been sort of making this assumption that objects moving to the right are positive and objects moving to the left are negative. Likewise, up is positive, down is negative. These are really common conventions. That's usually how we do it. Does it have to be done that way? Not necessarily, but many example problems you will see will use that sort of assumption. So again, so things that are vectors that we're going to be dealing with are going to be position, displacement, velocity, acceleration. And the reason that they're vectors, again, is because the direction is just as important as vectors. So I think I hit stop by mistake, but hopefully we saw what this is. Remember, the three blue lines are the average velocity. The red line is the tangent line to the graph. Its tangent at t equals 1 second, and so the slope of that tangent line would give you the instantaneous velocity at 1 second. So I really hope I didn't stop the sound a lot earlier. You're going to find that the average acceleration and instantaneous accelerations are super similar, but I thought that this video was long enough.